Hello, my name is Smits. This is a presentation on gradually typing strategies, which is work done in collaboration with Eelco Visser. Our story begins with Stratego. Stratego is a term rewriting language with programmable strategies for applying rewrite rules. Programming strategies is done through generic traversal primitives that can visit the children of any tree-shaped terms. Stratego is dynamically typed, which allows it to apply generic traversals without restriction. Stratego is used in the Stratego XT transformation toolkit and the SpoofX language workbench. Through SpoofX, Stratego is used at Oracle Labs, Canon, and is one of the technologies backing the conference website of Splash and other SIGPlan conference websites. Giving typing to strategies and generic reversals is a hard problem. There is work on a typable fragment, for example the Scrap Your Boilerplate papers. Our contribution in this work is a type system for the Stratego language as a whole. Let's look at the typical use case of Stratego to see the problems that stem from its dynamically typed nature. We start with a nice grammar specification from which we can derive a parser and a pretty printer. The parser will turn text that conforms to the grammar into a tree. The pretty printer is Stratego code that takes a tree that conforms to the grammar and turns it back into text. The code we write ourselves in Stratego is a transformation from one tree to another. This assembles into a nice little pipeline, and the problems only start to crop up when the transformation contains a bug. This bug in the transformation returns a tree, but it is ill-typed in that it doesn't conform to the grammar. Therefore, the pretty printer, which was derived from the grammar, cannot consume the tree. In the middle of pretty printing, Stratego fails to find the transformation rule for the ill-typed part of the tree. Due to attempting alternative rules and backtracking to alternative strategies, by the time Stratego gives up, it's rather difficult to find out where the problem originated. It might seem strange that Stratego allows ill-typed trees to be constructed in the first place, even if it is dynamically typed. To answer the question of why Stratego fails so late, we need to look at two parts of Stratego's design. One is an open world assumption. Signatures in Stratego are considered open types. There may be more constructors than a type in Stratego knows about. This is not necessarily a problem, as those constructors can be dealt with by generic traversals. The part we transform could just be a partial subtree. Generic traversals may also apply transformation rules that do not transform a well-typed tree into another well-typed tree, but after the traversal, the end result is well-typed. This is typical when translating from a tree of one grammar to the tree of another grammar. Each rule maps from one constructor to another, but leaves the children be. It is up to the traversal to visit the children and apply the right translation there. It's worth noting that, since Stratego allows ill-typed trees, people have used this ability to transform trees into ill-typed intermediate representations. Before I introduce the type system, it may be helpful to see what Stratego looks like, so let's look at an example of this last scenario. These are type definitions in Stratego. They've always been part of the language, and they define sorts, which are our types, and constructors. In this case, we have a description of abstract syntax trees for a tiny language. There are expressions such as variable references, integer literals, addition, subtraction, less than, unary minus, and increment. Possible statements are expressions, assignments, sequences of statements, while loops, and for loops. Rewrite rules in Stratego match a pattern on the left-hand side of an arrow and transform it into a pattern on the right-hand side. Here we have the sugar inc rule, which transforms an expression increment into a statement that increments the variable. While you can give a type to this rewrite rule, expression to statement, if you apply this rewrite rule to an entire AST, you get assignment statements inside your expressions. We actually do this in the first part of transform inc at the bottom by trying to apply this rewrite rule bottom up. The second part of transform inc cleans up the mess by finding from top down all the places where it can lift out the assignment to the statement level. This is done by the lift assign rule, which pattern matches on simple statements, a condition we will see later that selects for non-sequence statements. Then in the where clause, the onceTDHD strategy searches and replaces an assignment in an expression in the statement by a variable reference. Finally, the lift assign rule returns a sequence of the embedded statement from the expression and the transformed statement. Let's look at how these rules can be applied. If we apply the desugar_inc rule, we get the embedded statement inside the unary minus. This is an ill-typed intermediate representation. Then with our lift assign, we can lift it out again. Now we have a well-typed term. The lift assign rule uses a filter and a special strategy for finding the embedded assignment. The filter is just a strategy. Since any strategy can fail, the failure serves as the filtering mechanism. For a simple statement, we enumerate the constructors of statements that are not the sequence statement. The question mark pattern combination is a matching strategy that succeeds if the given term matches the pattern, like the left-hand side of a rewrite rule. The less than plus operator is the left choice, which attempts the left-hand side strategy and only applies the right-hand side strategy if the left-hand side fails. The onceTD_HD strategy takes an argument and it passes this argument to onceTD, which is applied to any expression child of one of the simple statements. Again, we enumerate all the options, including the different expression children of the for loop. To understand what onceTD does, we need to have a look at some generic traversals. The transform_inc strategy also uses a number of generic traversals. A bottom-up generic traversal first applies itself recursively to all children of a term and then applies its argument to the term. All_td applies its argument to the topmost terms for which it succeeds. So it attempts to apply the argument, and if it fails, it will recursively apply itself on all of the children. Note how onceTD_HD used these constructor named strategies. Each constructor definition in Stratego gives rise to a congruence. This is a strategy named after the constructor that has an argument for each child. The arguments are applied to their respective child, as you can see demonstrated for the add constructor. While the example in the previous slides was the idiomatic style of Stratego programs of the past, you can of course write your own code differently. If you introduce an intermediate representation that embeds a statement in an expression with an extra constructor, you can write desugar rules that work with a well-typed intermediate representation. As a side note, while Stratego allows for terms to be constructed at runtime that do not strictly follow the defined signatures, there are a few static checks. Stratego checks that constructors are defined and used with the right arity. Local variables and strategy and rule names are also checked to be bound. Types are not tracked or checked, and that's what we add with our contribution. So let's look at what we need out of a type system for Stratego. First of all, since Stratego is a pre-existing language with significant amounts of code that need to keep working, we need a type system that is backward compatible. As you could see from the snippets of code so far, Stratego's syntax is fairly minimal, so we would like the addition of types not to interfere with that either. Generic traversals are at the core of the language, and we should be able to keep using them. Given the amount of existing dynamically typed code, we would like a usable migration path for adding static types to the code. Finally, the type system should be modularly checkable at the file or strategy level to fit into the framework that the compiler uses to make compilation incremental. The way we fulfill these requirements is through gradual types. The old code is implicitly given the type dynamic, written as a question mark, to keep backward compatible. We can slowly add types for a simple migration path, and the way this works is that we add runtime type checks, casts, to guard typed code. When the statically typed strategy or rule is applied to dynamically typed data, we insert a cast. Let's look at some examples to make this more concrete. There is no type inference for top-level definitions. We use top-level type annotations to make a rule or strategy typed. This is a trade-off between minimal type annotations and having a modularly checkable type system. In a typed rewrite rule, we have typed terms for our input and output patterns of each rule, so we can type check them. The first alternative is our correct version from previously, whereas the other two have some type errors. The second alternative returns a well-typed term, but it is an expression where a statement is expected by the type annotation. The third alternative, we have mistakenly repeated the var constructor, which makes this a pattern that matches an ill-typed term, not a well-typed expression term. Within a typed rule or strategy, the local variables do receive type inference. This allows us to reduce the number of casts that need to be inserted when variables are assumed dynamically typed. Generic traversals and other generic helper strategies are typically type preserving, or TP, when their argument is type preserving. Finally, to make sure we can prove to the type system that a rule is type preserving, we sometimes need a type test. This will check that a term is type correct and gives a match failure otherwise. In contrast, inserted casts will halt the program with a runtime error when the given term is not type correct. We have a prototype implementation of the static part of the type system. This prototype can type check gradually typed Stratego code, return errors and warnings, and insert casts. We use this prototype to annotate an existing Stratego codebase. The project is called Jasmin, a Java bytecode assembler language. The manually written Stratego code in this project is over 3,200 lines, spanning 36 files. Some intermediate representations already defined with 49 extra constructors that were not generated by the grammar specification. There are 146 different strategies and rules. This project consists of an assembler to Java bytecode and an AST interpreter of Jasmin code. We first review the evaluation of the assembler code. We added type annotations for the standards library that were used in the project, which were 74 in total, and then we started gradually adding type annotations for strategies and rules. We didn't always get it right the first time, but inconsistencies were quickly found by the type system. We ended up with 117 type signatures, 85 of which did not need the dynamic type at all. We didn't find any type errors or bugs, which was to be expected, as this assembler has been used for a couple of years now in a course where students throw any and every Jasmin AST at it. The code was mostly written with static type discipline in mind, which made it easier for us to add type annotations. The interpreter was more interesting to add type annotations to because it was used a lot less. We found a number of classes of type-related bugs. Inconsistent use of integer literals and strings containing those literals is a common problem in Stratego. While Stratego supports integer and floating point numbers, our parser returns parsed lexical syntax as a string, including integers and floats. A second source of bugs was pattern matching that was not specific enough. A child of a term would be captured in a variable when the rule in question should really have checked that the child was a particular constructor. Therefore, the rule with the bug would match to many terms, and the later alternative of the rule would not be tried at all. A final source of bugs we noted was around lists. The interpreter would in some cases use a strategy that gives back a singleton list instead of directly returning the element in it. In general, this part of the codebase had less static type discipline, which made it harder to add type annotations without doing refactoring. Since we want to keep our evaluation constrained to adding type annotations and fixing bugs, we refrained from refactoring to be able to add more exact type annotations. Our evaluation had to stop short of evaluating the performance impact of our added type annotations, because the prototype does not include the runtime components for the inserted casts yet. We have a design planned, but we do still need to finish the implementation. We want to do more than just keep the performance overhead of casts low, though. Now that we have added types to Stratego, we also mean to explore what we can optimize based on type information. Finally, we're working on integrating the prototype implementation into SpoofX. This will allow a wider audience to easily try out the new type system for Stratego. In conclusion, Stratego is an existing, powerful term transformation language that has seen use in a number of areas now. But while we can use and abuse its dynamically typed nature, We also run into type-related bugs quite often, and this can make development in Stratego painful. Stratego's generic reversals defy fully static typing, but with gradual typing we were able to sidestep the problem. The concept of type-preserving strategies brings extra type safety and preservation of type information, which minimizes inserted casts. Our initial evaluation was encouraging, showing that well-tested code was quite amenable to being type annotated, and that in less well-tested code, the type annotations could quickly identify type-related bugs. Finally, this is not the whole story. There's more details in the paper, including parametric polymorphism and the formalization of our core type checker/cast inserter. It is published open access and has an accepted and available artifact. I encourage you to check it out.